In this section, let's talk about some key features of hdfs, which include high availability, metadata persistence, federation, data replica mechanism, and etc. First is the hdfs high availability. The high availability of hdfs is achieved by using Zookeeper to implement active and standby name nodes, and thus solving the problem of single point of failure. Here, Zookeeper is used to store HA status files. Actually, the active name node provides services, and the standby name node synchronizes metadata from the active name node and functions as the hot backup of the active name node. As for metadata synchronization, well, the generated edit log is written to the local host and journal nodes at the same time. When detecting that the edit log on the journal nodes changes, the standby name node loads the edit log to the memory of its own and generates new metadata, which is the same as that on the active name node, and then metadata synchronization is complete. While the active and standby FS images are still stored in their respective disks and do not interact with each other, FS image is a copy of metadata periodically written from the memory to the local disk, so it is also called metadata image. And Zookeeper failover controller, short of ZKFC, controls active and standby name node arbitration. As a simplified arbitration agent, ZKFC uses the distributed log function of Zookeeper to implement active and standby arbitration and controls the active and standby status of name nodes through the command channel. We know that namespace maintains the metadata in memory to improve the processing speed, but data in memory may be lost if there's any fault. In hdfs, there's the metadata persistence mechanism. We see that FS image saves file images periodically, and edit log records user operations and is used to generate a new file system image based on the FS image. Here is the metadata persistence process. The secondary name node will obtain the edit log and FS image from the primary node. Here, note that FS image is only downloaded once during the initialization stage of namespace and will use local files in the future. Then, the FS image and edit log files are merged in the memory on secondary name node, generating a new FS image called fsimage.ckpt. This is called checkpoint. Then, the secondary name node will upload the newly generated FS image file to the active node. At this time, there's an original FS image file and a new checkpoint file, fsimage.ckpt, on the disk. The primary name node will roll back fsimage.ckpt to override the original FS image, and during the period, the primary name node generates a new log file called editlog.new to store user operations. Such file will be renamed as editlog every hour or when the size of it reaches 64 megabytes. The single active name node architecture causes potential problems in cluster scalability and performance of hdfs. When the cluster size reaches a certain level, the memory used by the name node process may reach hundreds of gigabytes. In this case, name node becomes the performance bottleneck, especially when hdfs is used to store ultra-large files, such as user behavior data on the internet, voice data, etc. The name node memory is insufficient to support such a large cluster. Here comes the federation. Federation means that there can be many name nodes in the cluster, and each name node maintains a namespace volume, including the metadata of the namespace and the block pool of all the data blocks of the file in the namespace. That is, each name node is responsible for only some directory in the entire cluster. For example, if name node 1 is responsible for the database directory, name node 1 is responsible for the metadata of all files in the database directory. Here, block pool is a group of file blocks that belongs to a namespace. Name nodes are independent. They do not communicate with each other, and the failure of one name node does not affect other name nodes. And data nodes are registered with all name nodes in the cluster to store data for all the block pools. And here is the data replica mechanism. Besides metadata high reliability mechanism, the data stored on data nodes also has its own mechanism. Here we are going to talk about data replica mechanism. First, we need to know how to calculate the distance between different servers. Actually, the distance of data on the same server is 0. That is, the distance of D1 and itself is 0. the distance of servers within the same rack is 2. That is, the distance of B1 and B3 is 2. The distance of servers on different racks is 4. So the distance of B1 and B2 is 4. And the distance of servers in different data centers is 6. Okay, we know that HDFS implements the 3 data replica mechanism, and the replica storage policy is as follows. The first replica is placed on the data node to which the file is uploaded. The second replica is placed on the node in a different rack from the first replica. The third replica is stored on other nodes in the same rack as the first replica. For more replicas, they are stored on random nodes. The main function of HDFS is to ensure the integrity of data, and it implements different mechanisms to ensure the reliability of components. First, HDFS supports rebuilding of the replica data on failed data disks. When the data node fails to report data to the name node periodically, the name node initiates the replica rebuilding action to restore the lost replicas. Second, HDFS supports cluster data balancing. The architecture of HDFS owns the data balancing mechanism, which ensures that data is evenly distributed to different data nodes. Third, the metadata reliability. In HDFS, the log mechanism is used to record metadata, and metadata is stored on the active and standby name nodes. The snapshot mechanism ensures that data can be restored in a timely manner in case of misoperations. Fourth, the security mode. HDFS provides a unique security mode mechanism to prevent faults from spreading when data nodes or disks are faulty. That is, when the node is faulty, the cluster changes to the security mode. In this mode, data on the HDFS is read-only. Other operations, such as creating and deleting files, will fail. After the disk fault is rectified and the data is restored, the cluster will exit the security mode. There are some other design features of HDFS. First, HDFS supports the recycle bin mechanism and allows user to set the number of copies dynamically. Second, data is stored as data blocks in HDFS. Third, user is able to access data on HDFS through Java APIs, HTTP, or shell. Here are some common shell commands listed in the table. For example, we can use -cat to display file content, use -mkdir to create a directory. For more details, we'd better conduct some practice following the lab guidance. Next are some new features of HDFS version 3. First, erasure code is supported. Erasure coding is a data protection technology. It is the first data recovery technology used in data transmission in the communications industry. It is a fault-tolerant coding technology which can prevent data from loss and solve the problem of HDFS storage scalability. Second, union based on HDFS routers is supported. HDFS adds an RPC routing layer to provide a combined view of multiple HDFS namespaces. This simplifies the process of accessing the federated cluster for the client. Third, multiple standby name nodes are supported. Users are allowed to run multiple standby name nodes. For example, by configuring 3 name nodes and 5 journal nodes, the cluster can tolerate the failure of 2 nodes instead of 1 node. Fourth, disk balancers are added to data nodes for load balancing. That is, HDFS supports data balancing between different hard disks on a single data node. If data imbalance occurs between different disks on each node, we can run the HDFS disk balancer command to balance data among disks on a node. In this part, we talked about some key features of HDFS. Next, let's see the read and write process of HDFS.